assessments because some very smart people, probably smarter than me, have created these saying this is what kids need to know, but then I modify, I change the problems, I add, or I make them harder or easier or whatever. So essentially, what you should be ready to do is scaling of number lines. So like where you have a couple of the numbers on the number line, you need to fill in all the other missing parts. Guys, am I wasting my time? Should we just start the lesson? Because I have people totally like blowing me off right now. I'm trying to help you prepare for the test. Plotting points, like given the x and y values, but you also have to create the axes. Hey, Braylon, can you just stop that? Thank you. Sorry, I made the general class announcement and it didn't sink in, so like you're the one totally blowing me off right now. So setting up your axes, labeling your axes, guys, I'm also trying to tell you what kids have missed in the past. Like if you forget to label your axis, it doesn't really tell you anything. Putting values on your axis, so scaling that, like on an XY graph, so where you have to determine like how to make that. Some more probability, some more proportional relationship work. So like if it takes me 15 minutes to read 20 pages, how far can I read in an hour? Like that, those sort of questions. Adding positives and negatives. Adding and subtracting, multiplying, and, well, not really dividing yet, but adding, subtracting, and multiplying with fractions is on the assessment. Converting fractions, decimals, and percents. So being able to convert fluidly any direction. So if you're given the fraction or given the decimal or given the percent. Solving for an unknown. So in your homeworks where it's like, let's play the guess my number game, that's solving for unknowns. That's like solving for variables. Improper fractions, rewriting those as like a decimal or a percent, which is weird. An improper fraction is always going to be over 100%. So take like 11 over 10. That turns into 110 over 100, right? That's over 100%. It exists, but in certain cases it's not appropriate to talk about. So like, I'm giving 110% effort. No, you're not. That's a lie. Like, you can't. You'd be dead, right? Like, you cannot give over 100%. That's everything. If I give you more than everything, then I lied before when I told you that was my everything, right? So you like, but percents over 100 do exist. Just sometimes they don't make sense to talk about. More multiplying fractions, distributive property. So like, if you have things in parentheses and you're trying to multiply, you don't have to distribute, but you have to like order of operations or use the distributive.
Please come to the office. Nora Schwartz.
And that's pretty much it. Any questions from last night's homework? Starting chapter 4, pretty easy. Okay, so today we're working on scale drawings. So, if you could put a header on your paper, that would be fantastic. Giant stack of graph paper over there. Graph paper has moved. I made it less awkward because I realized it was awkward if I'm sitting here and you go to get graph paper here. It's weird, right? Sometimes I don't think about these things until we're actually in the moment. But graph paper's over there. Did I talk about geometry templates yesterday? No. Okay. These are now sitting out as a resource for you guys, but you cannot take them out of my room. AOR extensions, it's okay if you're in the pod, but these cannot leave. These cannot. I don't even have a class set. So like if we try to use these together, we won't have enough for everybody. They have like every shape we're going to use this year, as well as a protractor on the bottom, as well as inches on this side, centimeters on this side, and a positive negative number line on the top. So if you need to put a number line in your paper, like it can help you like, okay, mark there. So these are available for your use. You don't understand what this is yet, but it's tangent lines to a circle, which you probably don't understand what tangent is. But you can use those, and then pencils have moved too. I just put them over on that table because it makes more sense. So just general class announcements. So, has anyone ever heard like blueprints? Yeah, I hope so, right? So, what's a blueprint? George, what's a blueprint? A drawing of what we're going to build. Okay. Is it the same size? It's a big roll of paper, right? If you're going to make your drawing the same size of what you're going to build, it's going to be a giant drawing. Savannah, you have your hand up. What were you going to say? Yeah.
It's a non-to-scale drawing of something you're going to build.
No, wait, what do you mean not to scale?
It's not to scale as in that big blue piece of paper isn't going to be as big. Say you're building a house, it's not going to be as big as that house. That would be wasted. So it's basically kind of like unit, like say a little square on a paper is a unit. It's the same units. Say like a house is a 14 foot by 20 foot. That's small.
Tiny home.
Reduce it down to it to be able to fit on a paper, so you can write down what the dimensions of the house and
Dimensions. That's one thing George didn't say was dimensions on there. Now, I disagree with one thing you said, but it's a dangerous thing that society has kind of set you up in a trap. So, when we say not to scale, it's actually kind of dangerous to say. What that means is it's not the same size, but being scale of something means there's a ratio relationship. So if you've ever built a model car or a model whatever, those are often at a scale or like a train set, like at home. I don't know, maybe you guys are too young. But those have different scales of like it's 1 to 40 or 1 to 50 or 1 to 70 or 1 to 100. It's this thing that I have, the little bitty train, compared to the real thing, right? So when we talk about scale drawings all involve a ratio. And actually, I'm curious what the definition says. Aha, scale factor. So scale drawing. Go ahead and write down scale drawings. You should have it in your header, but we can put a definition here. Scale drawings are, I'm trying to figure out how to say this with the least amount of words. Differently sized and actually, well, scale drawings have to be a drawing, but you don't have to be a drawing to be scale. You could actually be a three-dimensional shape. Connie, you can get this right now. Differently sized drawing to represent the actual. I don't know why I capitalized actual. So I'm just honest with you guys. Maybe because I went to a concert. So scale drawings could be the same size. It might be. If I'm building a doghouse, I might actually draw it out on my poster board or something, and this is how big the doghouse is actually going to be. I did that when I made cornhole boards for the college I went to. I drew, and actually this is really nerdy, but I used, like, I made graph paper on a poster, like I made it myself, and then I cut out an OC to make it look, so picture block O. I did not go to Ohio State. I stole the block O for Otterbein. And then a C, like within it, but it had like nicer corners. Sorry, this top corner was angled. But so I used the scale drawing to scale down what I wanted or scale up based off, okay, I drew this on little graph paper. I like it. Now I'm going to make it bigger, blow it up, give it a scale factor. Now I'm going to do the actual. So we always use the scale factor. We talked about scale factor yesterday, right? Okay, it is like the multiplier. So it could be any number. It could be less than 1, which means shrink it. It could be bigger than 1, which means blow it up. But it can be any number that tells you what to multiply by. So when you look at maps for different things, and sorry, I think we're going to need rulers, so at some point I'll have you guys get rulers for your group. A map is always going to give you its scale. And do you know what the part of the map is that has the scale in it? And it also has what the icons mean and everything else?
it's like in the very corner. It has like something.
What's it called, though? It's the key. If we look at the key in a map, which I used to have a map hanging over there, but I have one right on the other side of that wall outside, out in the hallway. If you look at a map, normally at the bottom right, sometimes bottom left, there's a key that tells us 1 inch on this map, when you measure, actually equals 5 miles. And guys, this is going to like kind of date me, I remember my mother and father sitting in the kitchen with a ruler measuring our route to West Virginia. Or not West Virginia, but through West Virginia to get to Virginia. We were going to Virginia Beach for vacation. And they were manually measuring to figure out where we should stay in a hotel. Like, how many miles, how long is it going to take? Because this was before MapQuest. And you don't even know MapQuest because you have Google Maps, right? This is before all of that. So people used to have to physically measure on a map to figure out how far they were going. So if you got told something was 250 miles long and 450 miles wide, Pennsylvania is a terrible state to drive through. It takes forever because it's huge. It's like a lot of forest, which is cool. But how big would that be on the map? So with your group, figure out if on the map 1 measured inch is actually 5 miles in the real world, if this is the real world size of Pennsylvania, how big would it be on the map? So give me like the new length times the new width, like you used to do length times width, whatever. It's fine, just now we got to do this problem. You look uncomfortable. Let's be comfortable. What? What?
Struggle for power.
I have a solution. Now Jessie looks like she's like on trial or something. All right, how do I scale this down? Does anyone want to help me, or should I draw cards? How do I scale this down? Because the map is obviously going to be smaller, right? Connor?
Get the mile divided by 5, because 1 inch equals 5 miles.
We got to divide by 5 because we're getting smaller, right? We're using the scale factor, and I'm going to divide by 5. And do I just divide by 5 and then I say, okay, this is going to be 50 miles on the map? What do I do also when I divide by 5? I also change my units. So this becomes 50 inches, and this becomes. Now, what we actually did there, and I would like you to write this work out on your paper, please. Write a, I need my graph stuff. Write 250 miles and then put it over 1, like make it a fraction. What we actually did was multiply. Remember, division doesn't exist. We remember that, right? Division doesn't exist.
Nothing, everything.
You are right. Nothing really exists. We made it all up. Oh! Thank you. Who wants $1 million? I had George's head up off his desk.
Not me.
Check it. This mathematician might get $1 million for solving a math problem. So, now, notice the headline, skepticism surrounds. Well, because mathematicians don't trust things that they haven't checked yet. So, there is, now if you want to learn more about this, you need to go Google Riemann hypothesis. But encouraging you, my advanced math students, there are 6 math problems, actually I think there's more than that have kind of been dubbed like the unsolvable math problems. They're questions asked by mathematicians that not that they don't have an answer, but no one has figured them out yet. Yeah, they don't have an answer yet. So, so look it up. We can't go deep. Excuse me, we can't go deep into it today. But this question, mathematicians have been trying to solve it for 160 years. Bernard Riemann lived a long time ago, and this mathematician, like Latia, believes that he has solved one of those problems. If true, if his solution is accurate, which is going to take a long time to check, like probably a year or two, no joke, because it's a really deep, dense problem. If true, he will be awarded $1 million. Yeah. George, I need to read into this. Mr. Estes just kind of threw this at me this morning. But there's 6 kind of like famous problems, and I think there's even more. But just talking about no, it's like that breaks certain math rules. But back to what we were doing. Check it. What's on the board? Check it out. Check whatever. We want to end up in what units? Inches. Here's how we use our scale factor to go any direction, either from the map to a draw, from the map to the real world, or from the real world to a map, or any scale drawing. I shouldn't even say map. We are going to multiply by the scale factor. So we take the original or whatever we have times the scale factor, and that will make our new value. But how I plug in my scale factor here is unique depending on the problem. I want to turn this into inches, which means I want to get rid of the label of miles. If I put miles on top, miles multiplies by miles, and I get miles squared, which is like area, right? Miles squared. But if I put miles on bottom, what happens when you have a value divided by itself? They cancel out, right? So miles on top and miles on bottom is going to cancel, and then when I put inches on top, it's going to take over. So I plug in my scale factor of every 1 inch is 5 miles, and I get 250 over 5 is my amount of inches, which comes out to be 50 inches. So that's how we use our scale factor, is always through multiplication and always setting up the fraction, the ratio. Any questions on how we do that? Because you're about to do it. Check out. Sorry, now that it's up on the TV, it's kind of hard for me. Yulia, whatever her name is. Suppose that she uses a map of Pennsylvania to determine the Valley Forge is 14 miles from downtown Philly. Did she measure 14 miles? If not, let's say she was using the map up here, that scale, how far did she measure most likely? So talk with your team real quick. Did she measure 14 miles, or did she measure something else that told her 14 miles? How far would that have been? This should be like a 1-minute conversation. Remember, your scale is 1 to 5. You don't really need to. Would a half get her there? All right. So hopefully our groups got to the same conclusion as Simon's group up here and saying she probably actually measured not quite 3 inches. Right, because 3 inches would get you 15 miles, so she probably measured something just below 3 inches, and she decided that was 14. So here's that statement, not drawn to scale. Now what it really means here is easy to see in this picture. Not drawn to scale doesn't actually mean, and so it does mean that it's not the same size. Like we know that. But what it really means, which line looks longer? The bottom line or this edge line over here, the side line?
They're literally the same.
They're not the same. I literally can prove it to you. Watch technology. Check it. This line from there to here. Oh, I thought I could rotate. If I rotate this up, that line is, I used to, it's, if I was in my other program, I'd be able to rotate, but I can't rotate here. It's actually longer than this line. That's what not drawing a scale means. Your 17 line isn't necessarily bigger in the drawing than your 15 line. Now, it should be, right? If we were drawing this appropriately, your 17 line should be bigger than your 15 line because 17 is a bigger number than 15. So, our job now is to help Guillermo out and take his not scale drawing and scale it. Now, what we know is his lot, which is like what your house is built on, is 56 feet wide and 100 feet deep. And the garage is 20 feet back from the street, so there's like 5 feet in here. Or, sorry, this is, sorry, I put that in the wrong place. This, sorry, is 20. And this is 8, right? So right over here is 8 as well. Here's your job. I'm going to give you a few minutes to do this. On your graph paper, which is why we always use graph paper, because we need both directions. So if you're working on line paper, you're going to need to grab some graph paper. We want to determine how big should I make my outline of the lot, which I don't think we probably want to use 100 squares because, one, that's a lot to count, but also I don't know that your page is big enough. So talk with your, now you don't have to agree. So when I say talk with your group, that doesn't always mean you guys have to choose the same thing, but talk out your ideas while you do this. Are you going to cut it down in half and make it 50 tall and 28 wide? Are you going to cut it down by like a fourth? What are you going to do to be able to draw this on your paper and then accurately place the house in there? So to scale. To scale means shrunken down accurately. It doesn't mean the same size. It means shrunken down or enlarged accurately. Does that make sense? So at the end, you should be able to tell me one box equals some amount of feet. What your scale is going to be that every box on your paper, like one unit, whatever, is some amount of feet. If you made it 1-to-1, you need 100 boxes by 56 boxes. Right? But I don't think that's a good idea. How about it? Do you understand the objective, Simon? Yeah? What are you saying? Yeah. Yeah, you're drawing it. Yeah, yeah. That's all I'm giving you a decent amount of time. You don't have to make the same choices, but just have that conversation as you're doing it. So you're going to have to use partials, right? because of the limitation of my paper. And I shrunk it down, but like, this is my quote-unquote paper. I'm not even 20 boxes long. Right? Like, I don't even have 20 boxes to work with. So if I take 56 divided by 2, I can't fit it on. If I take 56 divided by 3, I might be able to fit it on, but scale factors of 3 are sometimes tricky. So I take a scale factor of 4 and say every box equals 4 feet. Then 56 divided by 4 is 14. So you don't have to do the same thing as me, but I'm going to make this 14 wide. And if I'm using a scale factor of 4 or 1/4, depending on how you look at it, how many boxes tall should I be? Or deep, or however you're looking at this. 25, right? Because 100 divided by 4. That's 16. Oh man, I'm using like my whole paper here. Now I heard some people in conversation saying, well, we can't do that, right? Like 15 can't divide by that, or 17 can't divide by that. They gave you weird numbers on purpose. So let's start with the easy. Can 20 divide by 4? Yeah. So if I'm starting at this corner, I gotta go 20 feet in, 8 feet over. So 20 feet, if every box is 4 feet, well, 4, 8, 12, yeah, 5 boxes, right? So then I'm gonna go in 8 feet, which is how many boxes? 2 boxes. That's where my house is gonna start. Is anyone confused at how we're taking this from what we have in the book onto our graph paper? Is anyone just not doing it because you don't feel like it? Yeah, I got a couple of those. So then, sorry, go ahead.
So ours is 7 by 12 and a half. What is it? 2.5.
7 by 12. What's your scale factor? Did you do 8? 1/8? Yeah, it's gonna be kind of tough. So think about what numbers would work. I'm gonna help you guys out. So if we're trying to divide by 8, 15's kind of gross. But 16 would be easy. Now, I'm not dividing by 8, I'm dividing by 4, but the same thing happens. 15, not nice. 16 would be. So if it was 16 feet, I'd go 4 over, but it's just not quite there. So since it's missing a foot, it'll be missing a 1/4 of the box. So I go 3 3/4. 17 feet can round to 16 and be easy to work with, but then it's just slightly over. So it's going to be 4 boxes and another 1/4 of a box. So I go up 1, 2, 3, 4, and a 1/4. Any questions on that? Shoot. I don't know my next measurement. To go left. So let's label as we go. Right, this is 15 feet. This is 17 feet. Now I don't know my next measurement, but I can figure it out. So do you know how we figure it out?
I was thinking that we should try to figure out what the 38 is from the 17, then go across from the 15.
You're close. So I'm trying to turn the left, right? And go along like the front of the house or whatever. Got an idea? We know there's a 30 up here, right at the top of the house somewhere, or at the back of the house really. And we know there's a 15 here, which means the leftover section right here is 15 feet. So another, well, I have a quarter there. Now this gets a little weird. I need to go 3 3/4. But this is already a quarter, so now I need to go 3 1/2 beyond that. 1, 2, 3 1/2. So you need to make sure in the end that your line is at the right scale to be 15 feet. You with me? Really? Conceptually, you're just not doing it. It's okay. Like, if you're with me conceptually and you know that you can show mastery, it's okay. But it just makes me ask the question. My next edge, we know, is 38. Does 38 divide by 4 or 8 or whatever you're using easy? Probably not. But round it and then figure out how far away it is. So if I'm using a scale factor of 4, I'm going to do 40. That would be 10, right? 10 boxes. But I'm missing 2 feet. How much of a box is 2 feet? Yeah, half of it. So instead of 10 boxes, I'll have 9 1/2. Crap. This awkward 1/4 is really annoying. So if I go 1/2, I'm there. Then I need to go 9 more boxes. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So what I did was I took my 38 feet times my 1/4. That gave me, well, 38 over 4 to start. But then that gives me 9 1/2. So I went 1/2 here, and I was still a little bit under that. So then I went 9, and I just know I'm a little bit under that line. It's really a 1/4 under that line. Because the awkward 1/4 down here. And then, it's easy, I just connect everything. Because the rest of it is square. I don't have to count anything else. This runs all the way up to the back of the house. And then I label 30, and we don't know what this is, we can figure it out. It's 38 and 17. No. Sorry, 30 and 10 is 40, but what's 8 and 7? 15. So it's not 56, it's 55. Okay, now we get to the actual question. That wasn't the actual question. How big of a pool can Guillermo put in his backyard? Guillermo wants to put a pool in his backyard. Now, I got 2 different questions. What's the maximum size of a pool that he could fit? And if he wants to leave a border around the pool to make sure that people can like walk and not drown, what size pool should he install? And that's more up to you. But what's the maximum dimensions of a pool that could fit behind his house, which in the drawing is above the house? So essentially we're looking at this space. Take a couple minutes. I gotta try to wait. So it refers to the mass. Mass. I think maybe I should have had you guys start with a new sheet of graph paper for this and all of us would be the same size. Yeah. So for maximum, as Jesse just asked, it could go the entire width of his backyard, which is going to be how many feet? 56. It's given to us. We labeled it. But the question is, how deep is that? So I can count boxes: 1, 2, 3, 4, 5, 6 and a quarter. How do I get that to become feet? Whatever your scale factor is, right? So my scale factor is 4. So if I multiply that by 4, well, okay, 4 times a fourth, that's 1. 4 times 6, 24. So add one more, 25. So this is 25 feet. So the maximum pool he could put in, 64 by 25. Now, as soon as you walk out the back door, you're swimming. But now let's actually. I got a question for you guys up here. So let's just all look at mine. If we're going to say that Guillermo does not want people to immediately be swimming, if he's going to leave a gap behind and offset it a little bit, so maybe there's a swing set over here. If Guillermo decides that this if that now connects through there, I just didn't want to write on my 30. If that's the size of his pool, according to my drawing, what are the dimensions? Who can walk me through how we figure that out?
Oh wait, that's your identical.
Well, but do you know my scale factor?
Yeah, it's 4.
No, I just was setting you up a box that you had to convert. So guys, the biggest thing here is that conversion of like using that scale factor to go either way. Yeah, it depends. Like, I don't know what code is. So maybe based off like building code, we'd have to modify our pool and leave a little bit more space between the house, and maybe like it actually would have to be like this, like a longer kind of like Olympic. I'm not sure what building code is. But yeah, we could modify that. We have space for options. Or maybe he just goes to Walmart and gets the like set up on top of your grass round pool. All right, check this right here. What is the scale factor? Try to do this on your own. I don't even want you guys talking to each other for a moment. What is the scale factor here? Based off what I've highlighted, we should be able to figure it out. Anyone know? Braylon? Yeah, 1 inch equals 20 feet. Because they give us the dimensions of 20 by 25. The 20 has to relate to the 1, because 1 1/4 is bigger. So that's got to be my 25. So it's 1 inch to 20 feet, and we could then solve problems from there. That is all the time I have for today. So have a wonderful day, guys. I love your shirt. Which the new movie was satisfying. I liked it. The female Ghostbusters.